Imagine drifting through the silent void of space, surrounded by endless darkness, when suddenly a colossal shadow emerges before you. At first, it looks like any other starless region of the cosmos, but then you notice how even nearby starlight bends toward it, as if space itself is being swallowed. This isn't just emptiness. It's a black hole, one of the most mysterious and terrifying objects in the universe. And yet, instead of fear, it inspires awe. Because the real question, the one that keeps scientists and dreamers awake at night, is this: what lies beyond it? Black holes are not ordinary objects. They are regions where the rules of physics as we know them break down. They begin their lives as stars, massive ones far greater than our sun. When such a star reaches the end of its life, it burns through the last of its nuclear fuel, leaving no energy to counteract the relentless pull of gravity. With no force left to push outward, gravity wins, and the star collapses inward. The core shrinks into an incredibly dense point, a singularity, while the outer layers are blown away in a spectacular supernova. From that violent death emerges the black hole, a place where gravity becomes so strong that not even light, the fastest traveler in the universe, can escape. But black holes aren't just powerful, they are strange. Imagine a region of space where time slows down the closer you get, where light itself curves into spirals, and where the fabric of reality stretches to its limit. This isn't science fiction. It's what Einstein's theory of general relativity predicts. Black holes warp space-time itself, bending the geometry of reality like a weight pressing down on a trampoline. And the closer you move toward one, the stronger this effect becomes. The first boundary you encounter on your journey is called the event horizon. This is the ultimate one-way gate, the invisible border surrounding the black hole. Once something crosses it, whether it's a star, a planet, or even a photon of light, it can never escape. The event horizon doesn't have a physical surface. Instead, it's a point of no return defined by gravity's absolute victory. Outside it, light can still flee. Inside it, everything is trapped forever. So the event horizon is like a cosmic mask, hiding the true heart of the black hole, the singularity, where the laws of physics collapse into uncertainty. But even standing just outside it, strange things begin to happen. To an outside observer, time itself appears to stretch. Imagine watching a spaceship approach the event horizon. As it gets closer, it seems to slow down, moving more sluggishly until, right at the edge, it freezes in place. From your perspective, it never actually falls in. It just hovers at the brink, fading slowly into red as its light stretches to longer and longer wavelengths. Yet, for the astronauts inside that ship, nothing unusual happens at first. They cross the event horizon without noticing a dramatic boundary. To them, time feels normal. but in reality, they've passed into a realm cut off from the rest of the universe. This strange duality, where time itself behaves differently depending on your point of view, is one of the many enigmas of black holes. But the story grows even stranger the closer we move inward. Inside the event horizon, no path leads outward. Every possible direction points inward, toward the singularity at the black hole's center. This singularity is not just a dense core. It's a place where density becomes infinite, where space-time curves infinitely sharply, and where our equations simply fail. General relativity tells us it exists, but it cannot tell us what it's truly like. To understand it, we'd need a new theory, one that unites gravity with the quantum world. And that, for now, is the missing piece of the puzzle. Yet before we venture further in, it's important to pause and consider what it would feel like to approach such a monstrous object. If you were falling feet first toward a black hole, gravity would tug much harder on your feet than on your head. The difference in pull would stretch your body like a piece of spaghetti, a process scientists aptly call spaghettification. For small black holes, this deadly stretching would happen well before you reached the event horizon. But for supermassive black holes, the ones millions or billions of times heavier than our Sun, the tidal forces are gentler at the horizon. In fact, you could cross it without being torn apart immediately, drifting into the darkness with no warning that you've already crossed the ultimate boundary. It is only later, closer to the singularity, where the forces would grow unbearable. And this raises the central mystery. What truly lies beyond? Is the singularity a final, inescapable end? Or is it a doorway, an entrance to another universe, a wormhole, a passage through space-time itself? Scientists don't yet know, and that uncertainty makes black holes some of the most tantalizing objects in existence. Every discovery about them pushes us closer to confronting the limits of our understanding. Already, black holes have challenged the very foundations of physics. Stephen Hawking revealed that they might not be entirely black, that they slowly leak energy in the form of Hawking radiation, a faint glow caused by quantum effects at the event horizon. If this is true, black holes can evaporate over unimaginable timescales, eventually disappearing into nothing. But if black holes evaporate, what happens to the information they once contained? Does it vanish with them, violating one of the most sacred rules of physics, that information is never lost? This is the black hole information paradox, a puzzle that has haunted scientists for decades, and solving it could reveal not just the fate of black holes, but the true nature of reality itself. So, when we ask, what lies beyond a black hole? We're not just asking about what happens to matter that falls in. We're asking about the limits of space, of time, of physics itself. A black hole is not just an object in space. It's a frontier of knowledge, a place where the universe whispers secrets we are only beginning to hear. But this is only the beginning of the journey. We've stood at the edge, gazing into the abyss, learning the rules of the event horizon. In the next step, we'll go deeper, crossing into the unknown and exploring what happens when you truly fall inside. And there, the mysteries only grow stranger. Crossing the event horizon is like stepping off the edge of the known universe. For everything outside, time has frozen you at the brink. But for you, the traveler, nothing feels unusual, at least not yet. The darkness ahead seems no different than the space behind, but you've already crossed into a realm where the rules are written in unfamiliar ink. Every direction, every possible future, now curves inward, drawing you toward the singularity. Inside the black hole, escape is not simply difficult. It is impossible. The structure of space-time itself has tilted so dramatically that outward no longer exists. Even light, the swiftest thing in the universe, finds all possible paths bending inward. You are being carried not just through space but through time. For in this realm, falling toward the singularity is as inevitable as tomorrow arriving after today. The very fabric of reality is forcing you deeper. But strangely, the journey doesn't feel like a sudden catastrophe. If this is a supermassive black hole, perhaps millions of times the mass of the sun, the tidal forces near the event horizon are mild. You float forward, unscathed, though you know what awaits closer to the center will be far less forgiving. Your sense of time remains intact, but the outside universe looks distorted. Light from distant stars stretches, smearing across your view, red shifted until the universe itself looks like it is fading away. You are seeing the cosmos from a perspective no human has ever known, and perhaps never will. Now imagine peering outward. The universe appears compressed into a small circle behind you, as if all of space has been painted onto a shrinking canvas. Outside observers, if they could still see you, would never witness you cross the horizon. To them, you are forever frozen at the boundary. But you know the truth, you are already far beyond. The universe behind you is sealed off, separated by a barrier no signal can cross. What lies ahead is mystery incarnate. As you fall deeper, the curvature of space-time intensifies. The gentle tug begins to feel stronger, as if invisible hands are pulling every atom of your body toward the center. The difference in gravitational pull between your head and your feet grows more pronounced. Slowly, the stretching begins. Your body elongates, not because space is pulling harder on one side, but because space itself is being distorted. This is spaghettification in action, the fate of anything that dares to venture too close. For smaller black holes, this stretching would have torn you apart long before reaching the horizon. But here, in the presence of a giant, the process is delayed. You have time, perhaps seconds, perhaps hours, depending on the mass, to wonder, to imagine, to fear. Every tick of your perception is drawing you closer to the singularity, a place our mathematics can describe but not explain. So, what happens at the singularity? According to general relativity, the answer is unsettling. Infinite density, infinite curvature, a point where the known laws of physics collapse. But infinity is not a physical quantity. It's a signpost that our equations have reached their limit. It suggests that our understanding is incomplete, that some deeper theory is needed to reveal what truly happens there. Could the singularity be a literal point? Or is it something stranger, hidden beneath layers of physics we have not yet uncovered? Some scientists speculate that the singularity is not the end but a bridge. According to one possibility, the core of a black hole could connect to a wormhole, a tunnel through space-time that opens into another region of the universe, or perhaps another universe entirely. Falling into such a black hole might not mean destruction, but passage. You could emerge elsewhere, light years away, or even in a newborn cosmos, a bubble of space-time birthed from the collapse. It's an idea that excites the imagination, though no evidence yet confirms it. Another possibility is that black holes might lead to white holes, the opposite of a black hole. Instead of devouring everything, a white hole would only eject matter and energy, never allowing anything in. If black holes and white holes are paired through wormholes, then perhaps what falls into one emerges explosively from the other. In this sense, every black hole might be a doorway to creation. But again, this remains speculation, beautiful and haunting, without proof. What complicates the picture further is the nature of quantum mechanics. According to quantum theory, information can never be destroyed. Yet black holes seem to trap everything forever. If matter falls into a singularity and disappears, what happens to the information it carried? This is the infamous black hole information paradox. And the paradox grows sharper when we consider Hawking's insight that black holes slowly evaporate. If a black hole eventually vanishes into nothing, where did the information go? Did it disappear, breaking the laws of physics? Or does it survive in some hidden form, encoded in ways we don't yet understand? Some physicists believe the answer lies on the surface of the event horizon itself. Perhaps the horizon is like a cosmic hard drive, storing information about everything that falls in. The holographic principle suggests that our three-dimensional world might actually be encoded on a two-dimensional surface, and black holes might be the key to proving it. If true, it would mean reality itself is stranger than our imaginations. But here, inside the black hole, these questions are not abstract, they are personal. You are falling toward a destination no one has returned from. Will you be crushed at the singularity, destroyed by forces beyond comprehension? Or will you slip through a hidden passage, reborn in another world? The silence gives no answer. The universe beyond the event horizon is deaf to your cries. Still, the mystery persists, pulling us closer with every discovery. Black holes are not just celestial objects. They are laboratories of the impossible, testing the limits of time, space, and knowledge itself. And while we may never truly fall inside one, our equations allow us to imagine, to sketch the outlines of a journey humanity has not yet taken. So far, we've crossed the threshold and entered the unknown. But to truly understand what lies beyond, we must look not only through the lens of relativity but also through the strange, flickering world of quantum mechanics. And when the two meet, black holes reveal some of their strangest secrets. As you continue your descent, the singularity draws closer. General relativity insists that this is the end of the line, a place of infinite density, where all known laws of physics break down. But physicists are rarely satisfied with an ending that offers only silence. So they've asked, what if the singularity isn't the end at all? What if it's a bridge? This is where the idea of wormholes enters the story. A wormhole, in theory, is a tunnel through the fabric of space-time itself. Picture space and time as a vast sheet of paper. If you fold that paper in half, two distant points can suddenly touch. A wormhole would be like poking a hole through the sheet, connecting those points. If such a structure exists, then the singularity inside a black hole might not be a dead end, but rather the entrance to a passage leading elsewhere. Perhaps across the galaxy, perhaps across the universe, perhaps even into a completely new one. The notion isn't just fantasy, it emerges naturally from Einstein's equations. Solutions known as Einstein-Rosen bridges describe tunnels linking black holes and white holes, theoretical counterparts that spew out matter and light instead of pulling it in. In this picture, every black hole could, in principle, be connected to a white hole through a wormhole. Matter falling into one would not vanish, but instead be expelled from the other, somewhere else in space-time. But there's a catch. These bridges appear unstable. The moment anything tries to pass through, they collapse. Without some exotic form of matter, something with negative energy to hold the tunnel open, the wormhole would snap shut before any traveler could make it across. Exotic matter remains purely hypothetical. We don't know if it exists, let alone if it could stabilize a cosmic tunnel. Yet the possibility lingers, tempting us with the dream of shortcuts through the universe. Still, some researchers take the speculation further. What if black holes are not just tunnels within our universe, but gateways to others? Imagine that when a massive star collapses and forms a singularity, the crushing pressure doesn't end in destruction but instead gives birth to a new bubble of space-time. From our perspective, this bubble is hidden inside the black hole. But from within, it could appear as a brand new expanding universe. In this view, every black hole might be a cosmic seed, each one sprouting a new universe beyond our reach. Our own cosmos could even have been born this way, from the singularity of some parent universe long gone. If this is true, then black holes are not only graveyards of stars but also cradles of creation. They would be both endings and beginnings, destroyers and creators. And the question of what lies beyond a black hole would take on a startling new meaning. Perhaps the answer is everything. Then there is the idea of the white hole, a mirror image of a black hole. Instead of pulling matter inward, a white hole would only push matter outward. Nothing could enter it, only leave. If black holes consume the universe, white holes expel it. Together, they could form a cycle of cosmic recycling, with matter plunging into one side and blasting out of the other. We have never observed a white hole, but mathematically, they are allowed. Some even wonder if the Big Bang itself, the sudden eruption of energy that gave birth to our universe, was a white hole event, the outpouring of matter from some parent black hole beyond our comprehension. Of course, these ideas are still speculation. The universe has never shown us a wormhole or a white hole. All we have are equations, models, and imagination. But they remind us of something profound. Black holes are not simply prisons of gravity. They might be portals, doorways, engines of creation, or threads that weave universes together. The possibility of wormholes has also inspired another intriguing question. Could an advanced civilization ever use them? If exotic matter could be found, if wormholes could be stabilized, then perhaps one day they might serve as cosmic highways, allowing instant travel across galaxies. Science fiction is filled with stories of ships diving into black holes and emerging light years away. For now, it's fantasy. But fantasy has a habit of becoming science given enough time. Just a century ago, black holes themselves were thought to be absurd. Now we have captured the first image of their shadows. Who knows what the next century will reveal? But there's another layer of mystery. If black holes are tunnels, if they connect to other places or even other universes, then what happens to time inside them? Does it flow as we know it, or does it fracture, splintering into new dimensions? Time near a black hole already behaves strangely, slowing down as gravity deepens. Inside, it may cease to resemble anything we understand. A traveler passing through a wormhole might not only journey to another place, but also to another time. The future or the past could lie on the other side. And yet, perhaps the most haunting possibility is the simplest one, that nothing lies beyond, that the singularity is truly an end, a place where matter and information are crushed out of existence, that falling into a black hole is not a journey, but a one-way ticket to oblivion. This is the grim vision, and for many scientists, it's the most realistic. But even this vision is not without its mysteries. If black holes destroy information, they challenge the very foundations of physics. And so the debate continues. What makes black holes so captivating is not that we know the answers, but that we don't. They are questions carved into the fabric of space. They remind us that the universe is far stranger than our limited minds can yet grasp. And in chasing their secrets, we are really chasing the edges of human understanding itself. So far, we've seen black holes as gateways, bridges, tunnels, cosmic seeds. But speculation can only take us so far. To go deeper, we must face the paradoxes that black holes create. And at the heart of those paradoxes lies one of the greatest puzzles in modern science: the clash between relativity and quantum mechanics. A clash that might finally tell us what lies beyond. As so far, black holes have revealed themselves as monsters of gravity, devourers of light, and possible gateways to other worlds. But the deepest mysteries they hold emerge not from the vastness of the cosmos, but from the tiniest scales of existence. For to truly understand what lies beyond a black hole, we must turn to the strange and delicate world of quantum physics. Einstein's theory of relativity paints black holes as smooth, continuous warps in spacetime. But quantum mechanics insists that reality, at its smallest scales, is granular and unpredictable. Normally, these two realms, gravity and quantum physics, don't overlap much. But at the heart of a black hole, where unimaginable density crushes matter into a point, they collide violently. And when they do, contradictions appear that shake the foundations of science. One of the first cracks in our understanding came from an idea proposed by Stephen Hawking in the 1970s. Black holes, he argued, aren't entirely black. Instead, they should emit a faint glow now called Hawking radiation. At first, this seemed impossible. Nothing can escape a black hole, not even light. But Hawking looked deeper, not at the black hole itself, but at the quantum vacuum surrounding it. According to quantum theory, empty space is never truly empty. Even the vacuum is alive with pairs of particles and antiparticles that flicker into existence and then annihilate each other, borrowing energy from nothing for the briefest instant before vanishing. Near the event horizon of a black hole, something strange can happen. One particle of the pair falls in, while the other escapes. To a distant observer, it looks as though the black hole itself is emitting radiation. Over time, an almost unthinkably long time, this radiation drains energy from the black hole, causing it to shrink. Eventually, after trillions upon trillions of years, even the largest black holes could evaporate entirely, leaving behind nothing but a whisper of their existence. But this revelation opened a Pandora's box of paradoxes. If black holes can evaporate, then what happens to the information about everything that fell inside them? Physics has a sacred rule. Information can never be destroyed. Burn a book, and its words vanish, but the information about the arrangement of atoms still lingers in the smoke and ash. Yet if black holes evaporate into featureless radiation, it seems the information they swallowed disappears completely. This is the black hole information paradox, and it has tormented physicists for decades. The stakes are enormous. If information can be destroyed, then the foundations of quantum mechanics, the most successful theory in science, are shaken. But if information is preserved, then how? Where does it hide? One proposal is that the information is somehow encoded in the Hawking radiation itself. Like a cosmic code, the faint particles streaming from the event horizon might carry subtle imprints of everything the black hole has consumed. But so far, we don't know how to read that code, or even if it exists. Another idea is that information isn't destroyed at all, but stored on the surface of the event horizon. This is the basis of the holographic principle, one of the most radical ideas in modern physics. It suggests that our three-dimensional reality could be like a projection from a two-dimensional surface. Imagine a hologram on your credit card. It appears three-dimensional, but the information is encoded on a flat surface. In the same way, the information about everything inside a black hole might actually live on its surface, projected into the universe around it. If true, this principle could mean that reality itself, the stars, the galaxies, even us, is a hologram projected from the edges of the cosmos. Still, no one knows the full truth. Some theories suggest that information is released slowly, woven into the Hawking radiation. Others propose that black holes might not completely evaporate, that when they shrink to a tiny remnant, they leave behind a final storage place for all the information they ever consumed. And there are even wilder ideas, that the paradox might be resolved by new physics we have not yet imagined, perhaps from a theory of quantum gravity that unites Einstein's relativity with quantum mechanics. But the paradox doesn't stop there. If information is preserved at the event horizon, then what happens when an object falls in? To the falling astronaut, nothing unusual happens at the horizon. They pass through smoothly. Yet to an outside observer, all their information seems smeared across the surface. This is known as the black hole complementarity principle, where two different but equally valid descriptions exist depending on the observer. From one perspective, you pass inside. From another, you never truly enter. Which is real? Both, perhaps. Reality, at the edge of a black hole, may be more fluid than we ever imagined. This leads us to another mind-twisting possibility, the firewall paradox. Some physicists suggest that, instead of passing gently through the event horizon, anything that tries to cross might be incinerated by a wall of energy. If true, this would shatter Einstein's vision of smooth spacetime and force us to rewrite our understanding of reality. Others reject this idea, arguing that it violates the very principles it tries to save. The debate remains unsettled, with no experiment yet able to decide the truth. And that is the haunting beauty of black holes. They sit at the intersection of our greatest theories, exposing the cracks in both. They force us to confront the fact that our understanding is incomplete, that the universe still keeps secrets far beyond our grasp. In the silent depths of a black hole, the fate of information, and perhaps of reality itself, hangs in the balance. For now, we stand on the edge of knowledge, peering into the abyss, armed with equations that both illuminate and confuse. Black holes are not just astrophysical objects. They are cosmic riddles, whispering that there is more to the universe than we know, perhaps more than we can know. And yet, our pursuit continues, because in chasing their mysteries, we chase the truth about ourselves, about reality, about existence itself. We've seen how black holes challenge quantum theory and relativity alike, hinting at a hidden order behind the chaos. But the story isn't finished. In the final step of our journey, we'll ask the ultimate question. Not just what lies beyond a black hole, but what black holes reveal about the destiny of the universe, and about the nature of reality itself. Imagine, for a moment, standing at the edge of the greatest mystery in the universe. Before you is a black hole, silent, invisible, yet infinitely powerful. We've journeyed through the science of their creation, crossed the threshold of the event horizon, and wrestled with the paradoxes they present. Now we arrive at the most profound question of all. What lies beyond? This isn't just about physics. It's about our place in the cosmos, and whether these cosmic abysses might hold the key to the deepest truths of existence. And as you'll see, the answer may change the way you think about the universe forever. Some scientists suggest that beyond the singularity lies not destruction, but creation. Black holes could act as cosmic wombs, giving birth to entirely new universes. Imagine falling into a black hole not as an ending, but as a passageway, a bridge to somewhere else. This is the baby universe theory, where each black hole in our universe might spawn a new universe on the other side. To us, the black hole seems like a devouring monster, but from within, it might look like a big bang, the explosive beginning of another reality. Could our own universe have been born from such a process? The idea is wild, but it lingers, refusing to go away. And the hook here is irresistible. If universes can breed, then perhaps the multiverse is alive with infinite worlds. Others imagine that black holes are not portals to creation but pathways. This leads us to the concept of wormholes, tunnels through space-time. If a black hole connects to a white hole, then in theory, information and matter could pass through the black hole and emerge elsewhere in the universe, or even in another universe altogether. While no one has ever observed a white hole, the mathematics of Einstein's equations allows for them. Could black holes be the hidden gateways we've been searching for, doorways to impossible journeys? The universe keeps its secrets well, but the possibility sparks endless curiosity. Of course, not all theories are hopeful. Some physicists argue that the singularity truly is the end. Matter, energy, even the laws of physics as we know them, collapse into something so dense and undefined that they cease to exist in any meaningful way. Beyond the event horizon, they suggest, there is simply nothing. No hidden universe, no bridge, no portal, just the full stop of reality. It's a chilling thought. But even this end of everything scenario raises profound questions. If the laws of physics break down inside a black hole, then perhaps our entire understanding of the universe is only partial, a shadow of something greater we cannot yet see. And then there's the information paradox, one of the most haunting puzzles in all of science. If black holes destroy everything that falls into them, does that include information itself? Stephen Hawking argued that black holes slowly evaporate through Hawking radiation, eventually vanishing. But if they disappear, what happens to the information inside? According to quantum theory, information cannot be destroyed. So, is it lost forever? Or is it somehow preserved, smeared across the event horizon in strange patterns, waiting to be decoded? If we could solve this paradox, we might not only understand black holes, but also unlock the foundations of reality itself. Imagine the key to uniting quantum physics and gravity lying hidden in the shadow of a black hole. That is the true prize and the true mystery. The deeper we go into this enigma, the clearer one truth becomes. Black holes are not just astrophysical objects, but philosophical mirrors. They reflect our own hunger for meaning. To some, they symbolize annihilation. To others, rebirth. To still others, an unsolved equation, daring us to keep searching. Every theory we explore, wormholes, baby universes, the information paradox, is as much about us as it is about the cosmos. Because when we ask what lies beyond a black hole, we are really asking what lies beyond the limits of human knowledge. Perhaps the real answer isn't about physics, but about perspective. Maybe black holes remind us that the universe is still vast and mysterious, that our greatest discoveries are yet to come. They are cosmic challenges, daring us to look deeper, think harder, and stretch our imagination beyond its current borders. Just as sailors once looked at the edge of the map and wondered what lay beyond the horizon, we now look at black holes and wonder what lies beyond the event horizon. Both questions come from the same place, a restless, unquenchable curiosity. And maybe that's the real gift black holes offer us. They force us to dream bigger, to imagine impossible worlds, to accept that there are things we do not yet understand, but that one day perhaps we will. Whether black holes are portals, dead ends, or seeds of new universes, they remain the ultimate frontier of human thought. And every time we look into the darkness, we're reminded that the unknown is not something to fear, but something to chase. So what lies beyond a black hole? For now, the answer is simple: mystery. A mystery deeper than the cosmos itself, one that pulls us in like gravity, refusing to let go. But maybe, just maybe, the greatest discovery is not what lies on the other side, but the journey of seeking it. Because in the end, it is not the black hole that defines us, but the questions we dare to ask about it. And if you've enjoyed this exploration, if you've felt the wonder of staring into the unknown, then stay with us on this journey. There are countless mysteries left to uncover, and together we'll drift through them, one question at a time. Because the universe is waiting, and so are its secrets.